So refrigeration, all right? You know, we could talk about it multiple different ways, but with it, it's always a closed loop, all right? There's not gonna be any entrance of any outside forces as far as like with these, any of the liquid or the gases that are inside, all right? So they're not going to leave. Nothing's going to enter. So you're not going to have leaks. You're not going to have lossage or anything else like that. All right. So you can kind of think of it almost like what we have here. All right. Where you have your engine's putting out work. Your heat source is adding heat to the system. Your heat sink is removing heat in the system, and the pump is adding work into the system. All right. Your highest temperature would be like your combustion gases. Your lowest temperature is your seawater. And it's always broken up into these four sections with refrigeration. You have your high pressure vapor, your low pressure liquid, high pressure liquid. All right. That's how it's always broken up. So you always have a line split through the middle. With this side always being the high pressure side and this side being the low pressure. And then again, split this way down the middle, with this side always being vapor and this side always being a liquid. All right. So I'm not the biggest fan, as I've said before, of engine, heat sink, pump, all that stuff. All right. With refrigeration, you kind of just have to dive into what it is. All right. So you have your working fluid, and this fluid, like I've stated, it cannot be removed. You don't add any, you don't lose any. It's always there in some way, shape, or form. All right. And what form that is what matters. All right. So you have your compressor, you have your heat sink, you have your metering device, which is your TXV. All right. As we know, it's a thermal expansion valve. And you have your heat source. All right. So we always keep it straight. Your heat source is where your food is going to be located. All right. And your heat sink is where it's going to be being removed. All right. Any of your heat that came from your food is going to be removed. Like I said, you have your adding of heat into your heat source. Your heat sink is removing said heat. Your lowest temperature for the entire cycle is going to be right here on this line, right before the heat source and right after the metering device. All right, from right before it goes in. From here to there is your coldest temperature. All right. If you actually look, if anybody works in, if anybody's worked in like some sort of like hospitality, or if they've seen larger chiller plants or anything like that of refrigeration, these parts of the pipe will usually be frosted over. It'll almost look like either ice will be forming on it, which isn't good, but usually you'll have a little bit of frost. It will be very cold to the touch. All right. And then you'll have your highest temperature from the exit of your compressor to right before it goes into your heat sink. That's going to be super hot. All right. Then you have your liquid side again and your vapor side split the same way. This side is always going to be vapor, just as this side is always going to be a liquid. All right. What it is on either side of it can change, where this side is always high pressure, where this side is always low pressure. All right, this exists as a low pressure vapor, but just on the other side of this compressor, you have your high pressure vapor, where work is being added to the compressor from an external source. That's going to be either done by an engine or electricity, but something is going to be adding work into the system via this compressor. All right. This metering device is going to be changing the state from a high pressure to a low pressure just due to how much that valve is open and how much it's letting through at a time. So as we go through, we have a really basic refrigeration cycle. We have our compressor. Like I said, it's a mechanical energy input. It's mechanical. It's putting energy into the system. It's putting work into the system. All right. And what you get out of it is a superheated vapor. We've used this word before, where you have your temperature chart, where you have basically a solid, then you have liquid, and then you have a vapor. All right. When you get up here on your vapor, this dot up there, if it will let me draw it, is past your liquid vapor line. And once you enter that position on your vapor line right here, you are no longer a mixture of liquid and vapor. All right, this would be a superheated vapor. It's, remember, you're starting to add temperature now. So if we called this water, all right, and that's steam, we would have 212 as our boiling point. So at this line, we would be having boiling water. It's going from a liquid and turning into a vapor. So as you get higher and higher and you remove all of the liquid, and as soon as all the liquid is now gone, you can start to actually increase temperature because you fully change state. So that's when you can actually go up in temperature. So you can get to 13, to 14. That's a superheated vapor. All right. Just how we would have a superheated liquid here. We have removed all of our solids, all of our ice. So the water you drink is a superheated liquid. All right. And you always have to think about this is that, you know, superheated doesn't mean that it's going to be 1,000 degrees. You can have a superheated vapor at like negative 32 degrees. You can have a superheated vapor at 15 degrees. So you have to think about it when what state it is, not into the reference of the actual physical temperature. Superheated vapor cannot burn you sometimes, whereas sometimes it will give you first degree burns, such as our 600-pound steam cycle on the ship. All right. But if you get superheated vapor on you in a refrigeration cycle, you can get frostbite. So move into our condenser, and the job of the condenser is to turn it from a vapor, and it's going to turn it into a liquid. All right. It's also removing not only the heat that was added from our compressor, but all of our heat that was added from our evaporator. All right. That's what our condenser's job is to do. Remove the heat of compression and to remove especially any heat that was added from our evaporator. So it is now turned into a liquid. It's a subcooled liquid. All right, same thing as a superheated vapor. It's subcooled. It's below freezing or its freezing point. All right. We're still on the high pressure side. Actually, no, we've now entered we're still on the high pressure side. Sorry, split here with vapor liquid. So now we're into the receiver. All right. If anybody remembers from last semester, the point of the receiver is a couple of things. First of all, in larger systems, you'll have a receiver. But in smaller systems, such as like your refrigerator, your car's air conditioning, your household air conditioning, stuff like that, you're not going to have a receiver. But in large refrigeration cycle plants, you will most definitely have one. And the whole point of them is to have a couple of things. One, it can hold all of the liquid refrigerant in the entire system right there. That's like what they have to do, be able to do. They can hold all of the liquid refrigerant for the entire system at one time. All right. Number two, this is while it's actually working and the system is running. It gives almost like a surge tank ability to it. All right. So it always has liquid refrigerant ready to go into the TXV. All right. If this calls for more refrigerant, you can put it in through your receiver. Your compressor won't have to turn right away on. All right. So almost gives like a surge tank. And then number three, it allows you to see the flow of liquid and it allows you to see that the system is working. You shouldn't be seeing any sort of it shouldn't be bubbling. You shouldn't see like air bubbles coming up from the bottom. Like if you see air bubbles coming this way, that's not good. All right. But it allows to give you a visual of what's actually happening inside of the system, especially at this point, is important. So from the receiver, we're still liquid when we go to our TXV. All right. And then at the TXV, we have almost called a needle valve. And it's called a needle valve because it actually has a needle point to it. And it's only going to allow a small amount of refrigerant to go through, just like our freshwater generation plant. We had one side was high pressure and it was going into a flash evap. We were only letting in a certain amount and it's now going into a vapor chamber. So now instead of going from a high pressure side of a pump and we are going into a vapor chamber that has a solid vacuum in it, we are now using a very small valve to allow a certain amount of refrigerant through. So that way we maintain a low pressure because this is now entering the low pressure side. It's going to change state a little bit. All right. You're going to have a small amount of vapor there. But really what you're going to have is going from a high pressure liquid to a low pressure liquid. And that's where you're going to be gaining that advantage of the refrigeration cycle. All right. This is what really makes it work, is that thermo expansion valve. This allows it to get cold and to become cooler than whatever you're trying to remove the heat of in your evaporator. So we go into the evaporator, and the evaporator is going to be pulling in because it has a cool liquid. The goal of the evaporator is to turn that cool liquid into basically a vapor, a low pressure vapor. It still will be cold to the touch, but it will be warmer than this side because it's removing all of that heat of the vegetables or the beer, or whatever you're trying to cool at that time. All right. And then as it sends it to the compressor, it's going to be a 100% vapor. but at a low pressure. And then basically the cycle just keeps going and going and going. All right. If we didn't get all of that, don't worry. We have 30 some odd slides for you to get it. All right. That was just a brief overview of all of those components. So the metering device, or the TXV, as it's most commonly called, like I said, the TXV stands for the thermal expansion valve. So this is basically what it has. You have an inlet here, and you have an outlet over here. You have your sensing bulb, okay? This sensing bulb is going to be filled with the same refrigerant as the system. Then you're going down a capillary tube, and that's going to be going on top of your TXV. Same way as we have with our regulating valves, we're going to be using spring tension. We're going to be using some sort of pressure on the top to be offsetting and trying to overcome that spring force to open up or close that valve. In this case, what we're having is a spring is going to be the closing force. All right, because our valve is upward seating. And we're going to be using the thermal expansion bulb, the remote sensing bulb, to heat up, send a high pressure gas over to the top because they're connected via this capillary tube. And it's going to overcome this spring force, and it's going to push open this valve. And it's going to allow more refrigerant to go through it and go through its outlet. All right. That's what's going on inside of this whole system. This remote sensing bulb we'll go over later in the slideshow of where it's located, but it's going to be on way into the evaporator. All right. But just know that the remote thermal bulb is going to be using the same refrigerant as the system. It's going to be using a capillary tube that's going to be sending that said refrigerant to the top of your regulating valve. It's going to overcome the spring pressure in order to open the valve. So this is the TXV on board the TSES. All right. See, you have your inlet, you have your outlet, and you have your sensing bulb and your capillary tube that's going out to your sensing bulb. Your sensing bulb is located like not just outside the picture, but it's going to be on the other side of that tube. All right. Now, these are the compressors that we have on board the TSES. If you remember what I said in class last semester, right here, there's 3 lines. I found out which side my freshman year, which side was the hot side accidentally by putting my hand right on top of it and gaining nice 3 lines right there. Don't do that. All right. So this is the compressors that we have and utilize on board. You don't have to have these memorized. All right. I'm not going to be looking for you to know that this is the suction shutoff and everything else. But this is some information for you if you want to take a look at it and get a nice visual of it, of what it is before you go out on cruise. So there it is. There's our motors that are actually going to be running it. And then here's our evaporator coils. So this is located inside of our reefer boxes, and they're going to be taking all of the heat out of the ice cream, out of all the food, name a food item that's going to be in there. It's going to be removing the heat that is coming from those food items. So let's talk about refrigerant properties. A couple things: has to be safe and a non-toxic, non-flammable, non-explosive, environmentally friendly. And this is the biggest one that was added within the last decade or two. All right, has to be chemically inert. It's non-corrosive, doesn't react with lubricants. Has to be detectable. So I know I said earlier that it won't have leaks. They're designed to not have leaks, but in case something breaks, you have to be able to detect it so it can be located. All right, some different tools that you can be using: a halide torch, dyes, soapy water. These are all things that you can use to detect these things. Basically, as destructive as you can be is probably with the soapy water. You're not going to, and the dyes. Basically, you're going to be using some sort of like a torch or a detector that you're just going to be bringing around, and you're going to be going onto the tubes themselves. Operating range: saturation conditions on high side and low side at a reasonable temperature and pressure. And economical: good pumping characteristics, good thermodynamic properties for absorbing and rejecting heat, compatibility with the compressor lubricants. So these are everything that it needs to be like meeting, like a criteria in order to design something. These are something that has to always exist inside a refrigeration. So operating range: saturation conditions on the high side and low side are reasonable temperatures and pressure. This is a refrigerant that is no longer in use, in R12. Okay, it has a really good boiling point, negative 21 degrees Fahrenheit. So R12 is a CFC. It's a chlorofluorocarbon. All right. It's a group of organic compounds containing the element carbon and fluorine, in many cases hydrogen, especially in chlorine and hydrogen. So basically, all what that means is that it's a chemical compound that, when released to the atmosphere, these CFCs are going to be attaching themselves to O3, which is our ozone. All right. They come in and they're very utilizing chemistry of their electron properties. They attract like magnets, almost like positive and negative magnets. And instead of leaving your positive and negative magnets as two separate entities, what it's doing is it's ripping apart O3, and it's permanently attaching itself to it and changing it forever. All right. It destroys the ozone, and that's why you always hear about how these CFCs are bad for it. I know we talked about it last semester, but CFCs are what they were used in everything. Like I said, in the 80s, women had those crazy, huge hairstyles. Those were brought up those were not because of CFCs, but CFCs were used in their hairspray. So women would be using that hairspray every day all across the country to make their hair stand up really big, and they'd be spraying the stuff into the atmosphere. So it's not even just, refrigerant leaking out into the atmosphere. It turned into, it was in, like I said, those spray bottles. You could be putting it in any sort of aerosol can that you needed. People who were, if they had problems with their cars and the refrigerant wasn't working, they could just, open a valve and blow it out into the atmosphere. It didn't hurt humans. It gives you kind of like a little bit of a headache, but that's about it. Again, considered a miracle compound. They used it for everything. Some older engineers told me this R12 was fantastic degreaser. If you needed to degrease like anything that you're using, some mechanical part, You throw it in the bin, you take a bottle of R12 and you just spray it all over it, and the thing would just degrease it. It cleaned it perfectly. Colorless, non-toxic, non-flammable. Basically, it replaced earlier substances. So if you're using like refrigerant in your house and it leaked, you would be using like ammonia, and that could kill your whole family and stuff like that. This leaked, like I said, you just kind of wake up with a little bit of headache, no permanent damage. Death is pretty permanent, considering with ammonia. Going through, as always, the first version of anything is never great. And they went from R12 to 114 and 114 to R502. And I think pretty much everyone is using 404 now and some sort of variant, or 114. So like we talked about, escape CFCs remain stable as they migrate high up the atmosphere. The chlorine CFCs break down the ozone layer, which prevents the Earth's surface from damaging UV radiation. These are some important dates, not only for my class, but for just of Coast Guard classes in general. They want you to know this. All right? They want you to know these dates because they're important. All right? You need to know that these things were banned. You need to know that you can still use them to 2020, 30. All right? And you need to know when these agreements were made. All right? Like I said, not just for my class, but for Coast Guard in general. You will see this on your refrigeration test come when you take your thirds license. And when you take your next semester, when you guys are in, well, not next semester, but in the spring, you take refrigerant. This is going to be on your examination for taking the EPA refrigerant examination, right? Which is all about releasing this stuff and having all these dates and facts memorized about this material. All right. So this is of course, of how we get better of what we do. We went from CFCs to HFCs, now to HFCs. All right. These were the worst. These are okay, but these were a good pathway to what we're doing. You can't even find 123 anymore or R22. This thing is great to work with. That one's really nice. And honestly, you're not even using 134A anymore. They're getting away from that. They're moving on to even better stuff. All right. 407 or 404 is really good. So let's go through. So basically just similar what they were just looking for. Get the same thing, but not damaging to the environment. All right. That's what they were looking for. They wanted to go from CFCs to HFCs. And of course, this mediator in the middle. They wanted to see if they can get something that was close to, but not exact, obviously, from one to the next. So that way you didn't have to change components so much. That's why you didn't have to redesign everything. You can do an R12 to R134A conversion in vehicles due to the fact that they're pretty damn close with everything that they have. A little bit off, but it's not going to make a big difference in the world. Those are similarities that we're going to have to look at. So, any questions so far? All right. And by the way, guys, like I, encourage you with these things. If you have central air in your house, after class today, take the time, go look outside, go look inside of what you have, you have a piece of machinery on the side of the house, especially if you have central air. All right. That's going to be your condensers outside, your compressors outside. Take a look at it. All right. Go up into your attic, see if you have the air handler up in your attic. If it's on, don't pull off a side panel. But if it's off, try and stick your head into a location and see what's what inside there. if you're using window air conditioning units, I know the back end of a window air conditioner comes right off. It's all right there. It's all exposed. Take a look at it. Try and identify parts with it. It will only help you going forward, because I can guarantee you're not going to be sitting onto a ship and, you're going to have some nice little pictures like this. It's going to be a jumble of pipes that are going to be full of insulation and lagging, and you're going to have to decipher what's going on. All right. But like I said, I can't force you. We don't have 540 lab for someone to show you around on it, but going through your own home is always good to just see what's what, especially now that we're entering into, you're not using water making in your own home, but refrigeration you can go look at. HVAC, electrical, you can always look at. All right. So from your compressor, you have your compressor right here. Like I said, adding work into the system. So it comes out of your compressor at 125 PSIG. So a high pressure is coming out. All right. Also, it's a superheated vapor, over 100 degrees Fahrenheit. It goes into your condenser. Like I said, not only are you trying to remove the heat of compression, but anything that's coming out of any of the heat was added from your evaporator. So as it goes through your condenser, it's using basically salt water to cool it down. All right. But I said a few moments ago, you have a condenser on the side of your house for your air conditioner. How is that removing heat? If it's super hot out, you're probably going to be using AC. So if your condenser is outside, how are you removing heat from it? You're just using the outside air to remove the heat. So what's going on there? Are we making physics happen in reverse? What's going on? What's the important numbers that are usually happening with that? If it's a hot day outside, say it's like a 95-degree day. Take a look at what we said with what's coming out of the compressor. How can we be pushing heat into a hot environment? So you'll be doing that because of what temperature that's coming out of your compressors at. All right. What's coming out of your compressor is always going to be hotter. All right. So you're going to be using, and they're built for this as well, obviously, but if you're using your air conditioner and it's a super hot day, it's 95, it's 110 degrees out, I guarantee you the temperature that's going to be coming out of that compressor is going to be hotter than that. Okay. It's going to be pulling in the heat, and you may have a slower heat transfer. But at the end of it, you will have a subcooled liquid on the other side. All right. So it comes out of your condenser as a subcooled liquid, goes into a receiver. So it goes through your TXV, and right here on your TXV is when it's going to turn in from a high pressure to a low pressure. All right. So as we see, we're in a receiver. It's 90 degrees Fahrenheit. And it's still at a high pressure. And that high pressure, as we go through a small valve, remember that's a needle valve, that thing is small. It dumps out on the other side at 2 PSIG, so we lose a huge amount of pressure. And from there, it drops in temperature. It goes down to negative 10 degrees Fahrenheit. And like I said, we had a small mixture. Some of it will go right to a vapor about 15%, give or take. So what's actually happening inside of that TXV? So under the right side, not German, it's not night, side pressure.
Go back one slide. Can you go back to that last slide? Okay, thank you.
Good. So, like I said, over here, it's 125 plus PSIG. All right. Then when it goes through this small orifice, it's just, I can't tell you how much. It's a small needle valve. All right. On the low pressure side, R134A evaporates at negative 10 degrees Fahrenheit. But each pound requires 90 to 100 BTUs of latent heat to change its phase. So what we're doing is we're using those facts right there. Each pound requires 90 to 100 BTU of latent heat to change its phase. So in cooling to negative 10 degrees, each pound can donate sensible heat in the process. It takes about 6 pounds of R134A cooling from 90 degrees Fahrenheit to negative 10 in order to create 1 pound of vapor, i.e. about 15% evaporates. All right. So what's going on here is we're going from a 90 degree Fahrenheit, 125 PSIG, and as soon as it goes through, it can't exist as basically it's evaporating at negative 10. But since it evaporates at negative 10, we are going from a liquid and we're trying to make it into a subcooled on a low pressure side. So again, we bring out these charts every time. What we're going to do, I'm going to erase some of the ink on the slide. So we're donating that because as we go through, we got to remember where we are with sensible and latent heat. All right, that's the important stuff. But this is a sensible heat line. Any heat gained here is called sensible heat. Any heat gained here is latent. So we're existing here at that negative 10 since it evaporates there. All right. And what's going on is that we're losing heat. So we go from 90 degrees Fahrenheit to negative 10. And it's donating that sensible heat in order to do that. All right. Because on this side, it's a low pressure side. This side is a high pressure side. And when it's at negative 10 on this side, it cannot exist as it was on the high pressure side. So it must lose heat that way. And it's losing heat. It's not going to the atmosphere. It's losing heat to the process. All right. It's not like it's going into the ocean. It's not like it's going into your hand if you would put it onto it. It's going, the energy is going into the process of changing its state, and it's going into the process of changing from a high pressure to a low pressure. All right. You're not just magically losing energy. So we then go to our evaporator. Hold on. In our evaporator, our broccoli is at 5 degrees Fahrenheit. All right, we're going to call it our freezer. We want it to be at 0. And the vapor liquid mix that's going into it is at -10. So we want 0. Our broccoli's at 5. And our vapor liquid mix is at -10 degrees. So in the evaporator, what's happening is that every single one of these turns in the evaporator is important. All right. This is a simplified version, but the amount of turns that you would have inside the evaporator correspond to what's going to be happening inside of it. And we'll go through it. All right. There we go. So the first loop as you go through is going to be latent heat being added into the system. All right. So it's just going along and it's not changing temperature. As you can see, we're going from -10 to -10 to -10 to -10. All right, on each curve. But what is happening is we're going farther along on this latent heat graph. All right, we're moving from here to here to here to here on each one of the curves. All right, but we're not changing temperature. So we're going from a 25% vapor, 75% liquid as it goes through its first curve. The second curve, it's a 50-50 mix. The next one is 80-30. And by the time it gets to the last run, we're at 100% saturated vapor. So we're existing right at this corner. It's 100% vapor, and we are about to turn the curve, and we are going to go into sensible heat region. So why do we need to go from, if we're ready at saturated, 100% saturated vapor, why do we need to go to -5 from -10? Why do we need to jump that last piece? Why do we need that sensible heat to be added? What happens next in the system? What's the next component that we're going to go and hit into? Anybody remember? From the evaporator, where do we go next?
Compressor or?
Yep, we go to the compressor next. So what happens in the compressor? Why do we need superheated vapor if we're going to the compressor next? The biggest thing to remember about compressors is that it can't handle liquid. All right, they tend to break when they start to compress a liquid. So we need to have a superheated vapor where no liquid will be present. All right, in order to make sure there's no liquid present, we need that superheated vapor. It goes through. Like I said, we need to go up to this point where it's -5 degrees. That's the important part. The entire time, we had no change in temperature because we were adding latent heat, but we are changing our phase. And at the last curve, we are going to be adding sensible heat into it, and we are changing our temperature now. And it goes off. We have a 0 degree Fahrenheit superheated vapor. Like I said, you have a superheated vapor right there that can give you frostbite if it was long enough. All right. And just on the other side, you'll have a superheated vapor that will burn the heck out of you. I know. Right on the other side of that compressor, it will burn your hand if you touch it. So as we talked about, we have our basic heat absorbed versus Fahrenheit graph that we use. All right. Liquid is over here. This is your whole liquid line. This is your vapor line, liquid vapor mix. All right. This is all latent heat. This is all your sensible heat. Okay. So as you go across, every single curve, like I said, is jumping from here to the next piece. All right. It's obviously not going up -10 to -7 and then jumping back down, but it's going across on this line. All right. Why don't I give you guys a 15, 20-minute break? All right. Let's reconvene at 10:45, and we'll go into the next part of this. Okay.
get it. Dad, when I say that things have switched hands, I mean to say that things you have previously claimed ownership of have transferred from your hands to my hands. In that, I bought your treehouse.
All right. Let's give it a couple more minutes for people to return. We'll start back up. So let's continue on. Like we said, we come out of the evaporator and we're going to a superheated vapor at that point. All right, -5 to 0 degree Fahrenheit. It's at 2 psig and it's going into the compressor. All right. That is pretty much the entire refrigeration system in a nutshell. But if we go into and look at what's going on, where I brought this up before. There it is. All right. So we have a sorry. All right. So we've brought up this chart before in the sense of last semester, where it's a pressure enthalpy chart. All right. Now, come on. Let's talk about enthalpy first. Enthalpy is the total heat content in a thermodynamic system, whereas entropy is the heat of disorder in the same degree. All right, so this is total heat. Contained in the system. All right. So as we look at this, we're looking and we're seeing that this is total heat increasing as we go along the x-axis. All right. And as we go up in the y-axis, our pressure is increasing. Let's take a look at what we have here. So this curve that I just drew separates certain physical pieces that are going on in the system at a time. All right, so up in this region that we have, I'm going to keep it blue. This is our subcooled region. Subcooled liquid region, sorry. All right. Over here, we have a superheated vapor. And then inside, we have a liquid vapor mix. So let's go through. I'll use orange. And you guys have seen, like I said, this before from last semester. It's a nice little famous chart. So as we go through with it, we have to recognize that each one of these four sides represents a component in our system. All right, so we have our compressor, we have our TXV, we have our evaporator, and we have our condenser. All right, those four pieces of equipment will fit onto one side of these. So first things first, what's the easiest component to start with to identify? Just looking at this chart, where's the one spot in it where pressure instantaneously changes? If I label them, it will probably help us all to identify it. Let's go with this kind of labeling. Keep the same. A, B, C, D, E, F. From where to where is going to be instantaneous pressure change.
F? Is it just shoots up or?
So it's going to be, remember, it's not a singular point, but it's going to be between those two. So this is where the TXV is going to be. Because we have an instant pressure change from one to another, from E to F is an instant pressure change. That's where it's going from a high pressure to a low pressure. So this whole side represents the TXV. All right. And then where's another location that we know in our cycle where we have a pressure increase, but it's gradual? And we also have total heat in the system increasing.
B to C.
From B to C, we have that, and that would be our compressor. All right. Now, the last two become a little bit more difficult because depending on which way we move our arrows is where it's going to go. But the one thing we can look at is what's happening on either side. All right. So what side is our high pressure? It's from the outside of, from halfway through a compressor, right, to what? The condenser or the evaporator, which is the high pressure side. We know our pressure is going to be high on the top or higher. Is our evaporator all right? E to C. Yeah, E to C is going to be our condenser. And last but not least, our evaporator is going to be down from so we know these points, but what do they actually mean for our system? So we look at it, first of all, let's put some arrows on it. As we look at what's happening inside of this whole system, we have to see that our total heat contained in the system is increasing on our x-axis, and pressure increases on the y-axis. So from B to C is existing in our compressor. All right, that existence in there, in that compressor, we are increasing our pressure. And we have a slight increase of our total heat in the system. You could see we have a larger Y in this direction. And as I drew that dotted line on the X, is showing our how much we've moved with our total heat. And then as we go and we leave our compressor, and we go to D and we go to E, we're going in our condenser. We are coming from a superheated vapor. We enter into a liquid vapor mix, and we come just into our subcooled liquid. All right. And from we enter and we exit out of that subcooled liquid, we go into our TXV. And instantaneously in our TXV, we drop pressure. And dropping that pressure, we are also dropping the total heat in the system. I'm sorry, the total heat in the system staying the same, but we were constantly dropping into that pressure. All right. And then as we increase our total heat in the system, our largest increaser is in our evaporator. So if we were to draw this out in comparison, to an actual system. All right, everybody remembers that's the compressor symbol at the top. So, as we look at this, I should add that in. All right. We get to see what's going on in this whole system. With our compressor, we come out of our compressor from B to C. Where would B be located in our quick little system diagram that we just drew? Roundabout location of B.
The top left corner.
Top left corner. So up in this portion.
Yeah.
Okay. Yes. Yes and no. All right. It can pretty much exist at B anywhere before the compressor and anywhere just as it comes out of the evaporator. All right. So this whole line can be 4 feet. It can be 40 feet. In theory, it can be anywhere on this. But as long as it's right before the compressor and it's outside of our evaporator. All right. Remember, from B to C is inside of our compressor. So let's put it right here. Let's put B there. All right. Get rid of those other two, though. So that leaves where C is. Like I just said, C is going to be on the other side of our compressor because the compressor is going to be adding entropy and it's going to be increasing our pressure. One last thing I should add is high pressure and low pressure side. So as we go through, let's do another easy one. Where is E located? That's just before the TXV coming out of our condenser. All right, that's going to be located again anywhere on the other side of our condenser. As long as we have a receiver right here, it would be on this side of it as well. So it's going to be here. All right, and just as it comes out of the TXV, it's going to be our location F. So this is where it starts to get, from here it gets complicated. So where is location A then? We know B is outside of the evaporator, but A is inside in our evaporator line. It's not a point outside of it, it's inside of the evaporator. So where would it be?
It's not on the last curve of the evaporator, is it?
It's going to be.
Okay.
But why?
That's where we, oh shoot, that's when we jump up in temperature, right? On the
Isn't that the my fault? Go ahead.
It's where we jump up in temperature. But what else is happening?
The super saturation. This one is the most saturated, right?
Well, it's not going to be, it's yes, it's 100% saturated, but remember it's 100% saturated vapor. All right, but also think about it is that we're no longer in that latent heat area. We have now entered into sensible heat. So if we look at that from A to B, we are going from a liquid, remember liquid vapor is existing inside of this curve, this blue curve. So this liquid vapor, we are no longer that liquid vapor at A. We are now 100% saturated vapor. And as we go from A to B, it's on that last curve, and it goes into the last curve of it. We are now adding all that sensible heat. And we are going to increase from that negative 10 degrees to negative 5 degrees to 0 degrees. And we're now turning into a superheated vapor. Does that make sense to you guys of where A to where B is? And that's why I said B, as long as B is outside, I could write B right here. And also write B all the way over here and anywhere in between. The condition doesn't change. But what's happening is now B is a superheated vapor, whereas A is 100% saturated, but it's inside the evaporator. And you add that sensible heat and you go into that superheated vapor region. Okay? Does the location of A make sense? Does anybody still need a little bit further explaining? Okay. So last but not least, let's talk about D. All right. So where's location D going to be? It's on, and obviously on the condenser line, but where in the condenser line?
Directly after it.
It's going to be directly after the condenser, like here.
Oh, wait, hold on. My bad. Right before it.
It's going to be at that point.
I think so.
So it's not going to be at that point. Remember, it's on the condenser line, but just how A is to B, C is to D. So B exists as long as it's outside the evaporator and before the compressor. Same thing with C. C exists as soon as it leaves the compressor and right before it goes into the condenser. So D is located somewhere inside of the condenser. All right. We are turning from a superheated vapor in the condenser and we're going into a liquid vapor mix. So it's where D is where the first molecule is going to be turning from a vapor, and it's going to be turning it into a liquid. And now with that one molecule that is turned into a liquid, we now have a liquid vapor mix. And we are still removing total heat. All right. And now we are no longer in that sensible heat region. Remember, the first portion of it, we're moving that sensible heat because we're turning from a superheated vapor into a liquid vapor mix. We have to go down in temperature. And now we're at our freezing point. Or we're at our, at our boiling point. And now from that point, we're going and we're staying on our latent heat curve. And we're staying in that liquid vapor mix. All right, that's where D is. It's just entering into that liquid vapor mix. Okay. So, does this whole chart here make sense to you guys? Okay, good. Anybody want me to go more in depth on it? All right. One last thing to add. I wish I could zoom out more on this. I'm going to do this. So we've talked about this last chart before. You kind of have to draw on this whiteboard in corners, and then it allows you to zoom out. Super weird, super annoying. All right. So we've talked about this before. All right. And these charts are going to show the last piece of the puzzle. And remember, we have our liquid here. On both lines, we have our vapor region up here. And these exist at different pressure levels. All right, so we have our high pressure chart on the top, low pressure on the bottom. All right, and of course, this solid line here is our liquid vapor. This is a liquid vapor mix. So let's write high pressure here. This is our high pressure line. This is our low pressure line. Now, let's talk about these same points. Where would A be on this region? What's happening? Let's not start at A. Let's start at, where's a good spot to start? You know what, let's start at C. I like C. C is in a superheated vapor state, right? And it's high pressure. So where does it have to be on these two lines? First of all, like I said, it's on the high pressure line, right? And it's superheated vapor. So what is that? Where should they be on this high pressure line?
Would it be the top of the vapor portion of the HP line?
So it's going to exist about around here.
Okay.
All right. It wouldn't be all the way on the top, but it's about like 5-10% up. All right. So that's going to be point C. All right. So that's in a superheated vapor position. It's going up in its sensible heat. We have now increased in temperature. So what happens when it goes to D? Like we talked about, D is in the condenser. And it's right when we start to have that first molecule start becoming into a liquid.
So it's liquid vapor. It's somewhere in the liquid vapor range.
Yes, but it's right at the border.
Right.
Our superheated to our liquid vapor. So where on our liquid vapor line should it exist?
At the end before we jump.
At the end before what? You broke up.
At the end of it, before it jumps up into the vapor portion of the line, like right at that corner, maybe.
It's going to exist right there. That's exactly right. All right, so we're going to go from C to D like that. All right, so from C to D to E, what's happening? Remember where E is on our picture of what's happening on our schematic. All right, E exists anywhere from the condenser right before it goes into the TXV. All right, that's where that point exists. So where would it be on our line? What happens inside of the condenser?
It comes out as vapor at the end of the condenser, right? Or no, my bad, other way around. It comes out as liquid coming out of the condenser.
Yes. So it comes out as a condenser. It comes out of the condenser as a liquid, right? So it's going to be on the liquid portion of our line. But if we look, we're still on this high pressure side. So we're still going to be on the high pressure line. All right. So through the entire condenser, we're going liquid vapor, and now we have entered into our liquid. All right. We're somewhere on this liquid line. All right. That's where point E is. So we jump from D all the way to E, all right, in our condenser. Now from E, to F. We're going through our TXV. We are going from high pressure to low pressure. What goes on there?
It turns into a liquid vapor.
It's going to be a liquid vapor. So it's going to be somewhere on our low pressure liquid vapor line. But whereabouts?
The beginning of it.
It's going to be somewhere in the beginning. Remember, it's at about 10 to 15%. All right? It's going to be transferred. Remember that whole 6 pounds of refrigerant to make 1 pound of vapor that we're going to be donating in that process? All right, so from E to F, we're going to a low pressure. And as we go to a low pressure, we're going to be donating not only the sensible heat to bring it in that temperature, but we're also going to be donating that latent heat in order to get 15% of a vapor, 75% liquid, but it's going to be in low pressure. All right. Remember, we're going up in that temperature. If we think about it, we're going up on that sensible heat. So we're adding heat into the process. We're donating heat in order to go up on this line. But up, we're not on the HP side anymore. We're going to low pressure. So we've donated that sensible and latent heat in order to make that happen. The heat went into the process to change its state. Does that graph help make more sense of what's going on in the TXV? All right. Anybody else think this stuff is really cool? Because I do. All right. So from F, we are now, like I've talked about, we're going from our TXV, and anywhere on that pipe, we're going to be going into our evaporator. So where does A exist on this line? A is from our liquid vapor mix just before it goes to a superheated vapor. So it's still on the low pressure side, so we're still existing on this LP line. So whereabouts? It's going to be
Is it where D is, but like on the low pressure side?
Yes. Exactly right. All right. So what's happening at that spot? We have a liquid vapor. It's 100% saturated vapor, and it's just about to make that turn. As soon as we add a little bit more heat, an ounce of heat that goes into it, we're going to be gaining sensible heat. We're going to be going up in temperature. That's why it exists right on that corner. All right. We make that next turn in that evap, we are going to be gaining sensible heat. We're going to increase in temperature. And so that means what? We're going to have a superheated vapor, but it's going to be a superheated vapor at a low pressure. So it's going to exist just about like C. There's B. And then B to C. All right, it's these three charts that will really show what's happening in a refrigeration cycle on every portion. All right. If you ever see these pressure enthalpy charts, which I'm sure you will see these again, not just in my class, but you will in thermo and everything through your engineering career here at Maritime, especially with refrigeration. Start with that TXV. All right. The only one that's going to be instantaneously going from a high pressure to a low pressure side. All right. Remember, enthalpy is the change in the total heat in the system. Okay. It's the total heat in that system at that time. Does these three charts make a lot of sense to you guys? Okay, good. It's easy for me to take a picture of this and post it to Blackboard, so it'll go up on Blackboard. All right, so that way you guys will have it as well. So let's just finish up on our PowerPoint, and I'll let you guys go for the day. I know it's a little bit longer, but we stop the sharing. Some days we have 30-minute classes. Some days we have a 3-hour class. Let's go here. All right. So as we talked about, capacity and performance of what's going on with the compressor. We have our heat source, which is our broccoli. It could be anything, all right? It could be whatever you just added into the refrigerator, all right? But it's the coefficient of performance is the heat transferred over work done. So the heat transferred is the heat that's coming from your heat source, which is your broccoli, and the work from the compressor is going to be pushing that, and it's forcing the heat to go into a hotter ocean. All right. So it's what you want over what you pay for. That is how you get the COP. So it's your tons of refrigerant times 3.5 over compressor kilowatts. All right. 3.5 is just one of those American conversion factors because we refuse to use imperial. You know, that's what you get. All right. So let's talk about refrigerant controls. Refrigerant controls, we have a whole bunch of things. All right. The TXV, like I said, we have a thermal expansion valve. That is being controlled by a sensing bulb. All right. And that sensing bulb uses the same refrigerant that's inside of these pipes. They do not touch each other. They do not mix. But they will have connection to each other via the pipe and the pipe of the sensing bulb. That's where the heat transfer is going to take place. They will not have physical contact with each other. The refrigerant inside does not mix with the refrigerant of the other, okay? Just like a normal heat exchanger, we're not mixing our fluids. So it senses the refrigerant temperature leaving the evaporator. It throttles the refrigerant flow to maintain a 5 to 10 degree outlet superheat at the evap. All right, so it's maintaining, the TXV's main job is to maintain the superheated vapor. So if you have too much refrigerant going through the system, that means you have too much cooling ability, which means that you won't be able to go into a sensible heat at the end on your last loop. And now you're going to have like 75% vapor, 25% liquid going to your compressor, which we've talked about is terrible. So if you have too much cooling capacity, that's where you end up in a problem. So this will be at a low pressure because it's not going to be gaining any heat out of there. So that low pressure is not going to be able to overcome that spring pressure. Remember what we said in the first slide. The spring pressure is the closing force, so it can't overcome that spring force. And now it's going to close your TXV. And now you have no pushing capability. There's no high pressure pushing on that low pressure to make it move. So now this large cooling ability is going to spend more time in the evaporator. It's going to heat up. And now you're going to have that nice superheated vapor going to that compressor. All right. And the compressor is going to suck it down. And it's going to turn into keep it on a low pressure side. All right. So if the TXV's job isn't controlling the temperature of this broccoli, I've made no mention to it. All right. It only cares about the superheated outlet temperature. That's the only thing it cares about. It's the only thing it's sensing. The solenoid valve is what controls the box temperature. So it's a temperature sensor that looks at the broccoli, not physically, and it's sensing the temperature inside of it. If it's too cold, if it's below 5 degrees of what we want it to be at, it will close. And it won't allow any more refrigerant. And everything that's on this side of the TXV and the solenoid valve will get sucked out by the compressor. Compressor is a positive displacement pump. It will pull everything out of there. It's going to be constant volume. All right. So the solenoid's valve only cares about the temperature of the box, whereas the TXV only cares about the superheated vapor. So it's a stop action valve. It's either fully open or it's fully closed. So we've talked about a lot at this point of everything getting sucked out. So that means we haven't talked about controls for the compressor. How does it know to turn on or off? All right. So you have your low pressure cutout. And it's kind of called a low pressure cutout, but it's really called a low pressure cut in, cut out. All right. So it senses on this side of the compressor, on the low pressure side of the compressor. So it sucks. So it senses the compression suction pressure and starts and stops the compressor under normal operating conditions. That's what it does. So if your box temperature is perfect, your solenoid valve is going to close, which now you have no more refrigerant entering into your evaporator. Your compressor is going to suck out all of your refrigerant out of that side. No more is entering into that side system because the solenoid valve is closed. So now there's no more to suck out. Well, you don't want that compressor to just keep running. So you use a low pressure cutout to know to turn off your compressor, and it's all based on your box temperature. Same thing with your TXV. All right. It's using the low pressure in the system to cut in and cut out the compressor. So if the pressure on that side becomes high enough, the low pressure cutout is going to turn on the compressor. And some water. All right. So that's the importance of that low pressure cutout. It's normal operating condition, but there's no connection. There's no physical connection to this solenoid valve. If this solenoid valve opens, it is not telling this LP to turn on the compressor. The low pressure side is only sensing the pressure, and that's what's going to turn on the compressor. All right. It's affected by the solenoid valve, but they're not connected to each other. Just how the TXV is not connected to the solenoid. But they all work together. They all do one job very, very well, and they allow the others to help it as well. So it starts the compressor around 3 to 5 PSI, and it stops the compressor around 0.5 to 1 PSI. All right. And then the high pressure is just a high pressure cutout. That's a danger scenario. All right. That is a situation where you don't want that side to build up to a high pressure. All right. And so it's sensing the compression discharge and stops the compressor under abnormal operating conditions. okay? Where the LP cutout is normal, it starts and stops the compressor under normal conditions. The HP is abnormal. That's an emergency device, okay? So it just prevents overpressurization of the condenser. It's not something you want to deal with. We got a few more slides, guys. Just stay with me. This is what they look like on the TSES. Very clean, very taken care of. Definitely no problems there. All right. So we've only talked about in this scenario one box. All right. And one box being like the evaporator. That's what they're called as freezer boxes or fridge boxes. People call them boxes because they're boxes you walk into. So what if you have multiple? And you can. Basically, what you're going to be utilizing is these things. Like I said, each one is controlled, and each one will have their own solenoid valve. And each one will have their own TXV. Because this is an evaporator, just like this is an evaporator. But they're evaporators to two different boxes. All right. The king valve's job over here is basically to just shut the system down. All right? It allows you to close the system and close it all off. All right. And that's why it's on the receiver side. So these solenoids are controlling the box temperature of their individual boxes. But if you're on a ship and you need to keep your broccoli cold for the entire 2-week-long journey across the ocean, but you don't want your beer to freeze, you need to keep them at 2 different temperatures. And the way you do that is the set point of your TXVs and the set point of your actual temperature in the box from your solenoid. If it doesn't need to be that cold, you're not going to be letting that much refrigerant in for that long. All right. So if we look at this, our evap for our broccoli needs to be freezing. All right. So the evap's at negative 10 degrees Fahrenheit or 2 psig. All right. So the temperature ranges anywhere from -2 to 8 degrees Fahrenheit. Whereas the evap for the beer fridge is going to be at 34 degrees Fahrenheit or 29 psig. And its temperature range is going to be anywhere from 34 to 44 degrees Fahrenheit. So we have right here superheated vapor at 2 different temperatures. And that's the craziness of this is what we have to do is if they're connected at this end of this line, this 40 degree Fahrenheit, 29 psig superheated vapor is that's going that way. This is a low pressure over here. How do we stop that? How can we have 2 boxes exist on the same line, even if they're running in parallel? How do we stop that backflow? Because we are going to go from high to low no matter what. From high pressure to low pressure, it's going to want to go that way. Somebody in the chat. There we go. A one-way valve or a check valve. We could have that. Come on. Well, in this situation, it's going to be called a back pressure valve. All right. So this is going to maintain the high temp chill boxes. All right. So what it's doing is it's required on everything that's higher than your lowest temperature box. So if we had more refrigerant boxes and only one freezer box, all of the refrigerant boxes would have these back pressure valves. All right, but our one freezer box would not, because it's going to be existing at a lower pressure. And all of the boxes that are at a higher pressure will need to keep that higher pressure contaminated and contained in that one box as evap. And the way to do that is with these back pressure valves. All right, it's a regulating valve that's going to maintain pressure on one side of the system. Now we have our king valves. Basically, like I said, these things are just going to be utilized in opening and closing of the entire system. All right. There's the king valve on the TSES. So we have refrigerant controls. So again, this is what we've always talked about with our regulating valves. All right. We are going to go and we're always going to maintain the outlet of our salt water, anything coming out of a condenser. If we don't maintain the outlet and we maintain and we regulate the inlet, and if we only let 50% flow going in, we would only fill this up to 50%. And now your cooling capacity is lowered. But if you only allow 50% out, this cooling water regulating valve only allows 50% out, this is still going to be filled to 100% with salt water. But it's going to have 50% of it flowing out of it. All right. So remember, big things. TXV only cares about superheat on the outlet of the evaporator. Solenoid valve only cares about the thermostat setting. It's going to open and close. No regulation. Back pressure valve is on the evaporator outlet of the high temperature boxes. So if you have a low temperature box, your lowest temperature box will not have a back pressure valve, because any of the other boxes, once they go onto the other side of their back pressure valve, is going to exist at that pressure and it will take care of it. All right. And it's going to keep that high pressure contained in its system. On the compressor, the LP cutout, like I've said, it's called an LP cutout, even though it starts and stops the compressor in normal conditions. Whereas the HP cutout is an abnormal, it's an emergency. And on the condenser, we have the circulating water regulating valve. And as always with any heat exchanger, it's always regulated on the outlet. And let's just talk quickly about system charging. And this is when you want to add any refrigerant into the system. All right. Basically, you have a couple of things here. If you're going to be adding liquid, you're going to go into the liquid side of the whole system. You want to enter it in on the other side of your receiver. And if you want to go to gas, you go into the suction side of your compressor. All right.
Go back to the liquid charging.
Yep. Pretty much with liquid, you're never really going to charge with liquid. You're almost always going to charge with a gas or a vapor, because then you can use the actual compressor to suck out the vapor out of your canister. All right. With the liquid charging, you're relying on the bottle's own internal pressure to overcome the pressure of your system. So you're going to get more out of it if you charge it with a vapor side. All right. So there's that. I know today was a lot. All right. I guess I encourage you guys to just take a look at your own refrigeration systems in your house. Everyone has a fridge, but you know, the parts are a little bit more exposed. You don't have to be messing with your fridge. and pulling it out. I know mine is stuck inside of a wall. I have to pull it out whenever I have to deal with it. You know, just take a quick look over your own equipment in your home. See if you can identify it. See if you can just kind of walk yourself through it. But if you guys have any questions, feel free to ask. Like I said, if you have questions throughout the day, like I said, I know today was a lot of information. I know it's all quick. So you guys are, as far as I'm concerned, you're good. Make sure you guys really try and get to class on time because those quizzes push us back. All right, because it's almost like 9:40 by the time we actually start with our lessons. All right, so make sure you guys get onto the Zoom. If you're having technical issues, I saw some of you guys were having that earlier. I see you coming in and out of the class. Not talking about you guys, I'm just talking about people who just come in late. All right, so this whole pressure enthalpy, all ABCD thing that we went over for like 20 minutes. I'm going to post that to Blackboard so that way you guys will have that. All right. Other than that, you guys are all set. So, like I said, if you have any questions, I'll stick around.
Have a good one.
Have a good one. You guys have any questions?
No, I'm good. I like the charts at the end with the entropy charts. It helped me understand it a lot more.
Oh yeah, it's these three really do a number for what you can, how everything works together. It's the full picture. That's why I like them.
Okay, enjoy the rest of your day.
You as well. Everyone else good? All right.